Good morning, everyone. My name is Anna Landreville. I am the lead scientist for building materials at Imerys. And today I will be giving a presentation about the impact of calcined clay particle size on performance in mortars. So just to give you a quick overview of Imerys, Imerys supplies a wide range of raw materials to different industries. In North America, we mine diatomaceous earth, perlite, and clays that can be used as pozzolans. We also mine calcium carbonate that can be used as a mineral filler. And we have minerals such as mica and wollastonite that can be used as reinforcing additives in cementitious systems. In addition to minerals, we have a line of specialty calcium aluminate cements, and several lines of admixture products. So like many other producers, our existing metakaolin grades are highly refined to meet the stringent purity and color requirements for the paper, paint, and refractory markets. So our goal is to develop a new generation of calcined clay products specifically for the concrete industry by utilizing clay stockpiles that don't meet the specifications for other markets. By eliminating unnecessary beneficiation steps, we can simplify the production process to be more streamlined. There are a couple of sustainability benefits to this project as well. First, it increases our natural resource efficiency by utilizing a larger amount of the crude that's mined. So if you see this picture down here in the middle, you can see that there is soil and other overburden on top of the clay deposit. And then there is a strip of this more red material. So that is the high iron content clays that would not be suitable for our traditional markets. But we think that we can use it here in the concrete industry. The other thing that is a sustainability benefit is that it provides a cost-effective solution for the concrete industry to reduce its carbon footprint. So there are two crudes that we utilized in this study that contain higher amounts of titanium and iron than our commercially available product. So our commercially available product here is designated MK1. And then the experimental ones are MK2 and 3. And if you see this picture at the bottom, the high iron content is evident in this darker material. So these crudes where MK2 and 3 are considered off-spec by our traditional standards. But since we're in the middle of the kaolin belt, we're a little bit spoiled, and our off-spec crudes still contain over 90% kaolinite. So after calcination, the samples were tested by TGA to quantify the amount of uncalcined kaolinite present. The experimental samples 2 and 3 contained higher amounts of uncalcined kaolinite because they were processed in pilot scale kilns, while MK1 was made on an industrial scale kiln where the process has been fully optimized, so it contained less unreacted material. In addition to XRF and TGA, the samples were analyzed by XRD, and no mullite was detected in any of them. So in addition to exploring off-spec crude sources and simplifying the overall production process, we wanted to determine the particle size distribution that would optimize both reactivity and workability. So we know that our commercially available grade has a very fine, narrow distribution that's ideal for other applications, but it can cause problems with water demand in concrete. So the experimental samples were milled using different processes to create coarser particles with a broader distribution. And you can see the sediograph particle size distribution here, where the experimental samples, which are in red and blue, They have an overall coarser distribution, at least on the top half of it, but they contain significantly more particles finer than 1 micron compared to the commercially available grade MK1. So the increased presence of those fines resulted in higher surface area values. The effect is also seen when you look at the steepness factor of their distributions, which we estimated by dividing the D90 by the D10 particle size. So these experimental grades are overall much broader than the existing product. So when I first wrote the abstract for this presentation, I was seeing a strange trend where the compressive strength of mortar samples was actually increasing as I increased the water content, which is of course not expected. So I asked several more experienced people on the topic, and they suggested pre-blending the cement and metakaolin with a high shear mixer. So as you can see, pre-blending those two materials had a very significant impact on both the flow and the strength development in mortars. When I was adding the metakaolin directly to water in the mixer, I believe it was agglomerating, which is why the flow values were higher, but the strength values were lower. So I just wanted to mention this because if there's anyone else out there that's new to the world of testing metakaolin, it's relevant. I also couldn't find anything about pre-blending pozzolans in the existing ASTM standards. It seems to just be something that people in the industry know, but maybe it's not clearly written out anywhere. So that might be a good topic to bring up in the future at ASTM as people start working with these materials more. So samples were tested in mortars using the ASTM C311 method, where the test mixes were prepared at 20 weight% cement replacement, and the water content was adjusted to produce flow that was equal to the control sample. Also prepared samples with a fixed water to binder ratio at 0.48. So you can see despite having the lowest surface area, the commercially available grade MK1 actually took the largest amount of water to achieve fixed flow. It also had the lowest flow value when the water content was fixed. When we look at the experimental samples, the sample with the broadest distribution, which is MK2, had the best flow value when the water content was fixed. And it also had the lowest water requirement to achieve fixed flow. Looking at the strength development, samples are fairly similar. At 7 days, the sample with the broadest distribution, MK2, had the highest strengths when the water content was fixed. When the water content was increased for fixed flow, the sample with the highest surface area, which was MK3, showed the greatest strengths. And then after 28 days of curing, the commercially available grade, MK1, had the highest strengths at the fixed water content. And then at fixed flow, the sample with the broadest distribution, MK2, had the best strengths, which is probably because it had the lowest water demand to achieve that fixed flow. So in addition to testing fixed water and fixed flow, we used an admixture and fixed flow. So the admixture here was one of our products called Compact 149S. That is a polycarboxylate ether chemistry. The admixture was dosed in to achieve fixed flow. So not surprisingly, the samples with the higher surface area, which are the experimental grades, they required a larger dosage of admixture to achieve fixed flow. This could also be because they had a higher amount of uncalcined kaolin, which could have increased the admixture dosage. The early strengths, when we look at this, the broadest distribution, MK2, had slightly lower strengths at 7 days, but after 28 days of curing, all 3 samples had very similar strengths. So in addition to mortar testing, the reactivity of these samples was tested using the new bound water method. So I believe that this has already been talked about, but basically using ACS reagent grade chemicals to create a synthetic pore solution, curing that for 7 days, and then putting it in an oven at 350 degrees to measure the amount of chemically bound water. I took it one step further and looked at the proposed R3 plus method, which adds an extra heating step going from 350 to 550 degrees Celsius to specifically look at the calcium hydroxide content. So here again, all 3 samples are performing very similarly. They also have very high reactivities. Got some reference samples included on the graph. See there's a sand, which is inert, still has a value close to 2. And then we've got silica fume and a fly ash as well for comparison. But again, all 3 of the metakaolins are outperforming the reference materials there. And the last thing that we did to look a little more closely at the reactivity was prepared pastes. So we mixed them exactly the same way that the mortars were mixed, used the same water to binder ratios, same cement replacement levels, and they were cured in the same way as the mortars. They were cured for 7 days before they were dried and milled. And then we tested them on XRD and dosed a known amount of an internal standard in there so that we could help quantify some of the phases by rebuilt refinement. So looking at this graph, we can see that the metakaolin samples have significantly less calcium hydroxide, which supports the bound water in the R3 plus test that was done as well. You can also see that the amount of amorphous material was quantified with the help of that internal standard. And there appears to be a slightly higher background along with a higher amount of amorphous material that would suggest the development of CSH gel in the metakaolin samples. We also found evidence of monosulfate and hemicarbonate samples or peaks in there as well that support the idea that the metakaolin is providing a pozzolanic reaction. So some of the conclusions here. I think this has been shown in other places as well, but we've shown that our off-spec crudes with higher amounts of iron and titanium are in fact suitable for the production of calcined clay. We've shown that minimal processing, reducing a lot of those beneficiation steps, can provide equal performance with the highly refined existing grades. We've also shown that a better flow value can be achieved with a broader particle size distribution without compromising the reactivity in mortars. So for future work, we'd like to see just how much coarser we can go with these and see if we can get any additional benefits in terms of flow before we start to impact reactivity. And then the other thing I'd like to look at is more durability testing to see if there's any difference, not just in reactivity here, but the durability benefits that they provide. That's it for me. Any questions?
Thanks, Anna. You do have a couple questions in the Q&A. I'm going to just try and pick one because we are, again, on a tight schedule today. There's a question here about your choice of keeping your water content constant rather than adjusting water content per flow. Can you talk about your decision-making process in choosing to do the experiments that way?
Yeah, I know that that's the way that C311 is written right now. And there's always this debate of, at ASTM and other places of what's the best way to go about it, because we did see that the performance decreased as we increased that water content. So we know that the European standards allow for the addition of a water reducer in there to take away that variable. And it's also more representative of the way that people would actually dose this material in the field. They would have a prescribed water content, and they wouldn't go above that. They would add an admixture in there in order to achieve the right flow. So that's why I chose to look at it both ways, was more of the existing ASTM standard, and then something that's maybe a little bit closer to how people would use this in the field.
Great, thank you. You